In this lesson, we introduce resistors in series and in parallel. Here are your objectives. So resistors in series look like this. They are lined up one after the other in a circuit, so that there's only one way for the current to go. The current passes through here, and the same current passes through there. I'm drawing the conventional current as if it's coming out from the positive terminal of the cell. So the current through resistors in series is the same. However, the potential difference across them is not. So think about potential difference again as the energy per unit charge, and that is increasing in the cell. So the cell, if you want to think of it this way, is like boosting it up a set of stairs. It's boosting the energy of the charges. And by conservation of energy, that energy has to be shed to get around the circuit and back to the start. It's like walking around the circuit and you have to get back to this level of energy. That means that the potential difference across the first resistor and the potential difference across the second resistor have to add such that in this circuit they equal the potential difference across the cell. So the potential difference across resistors in series adds to the total potential difference, in this case the terminal potential difference of the cell, meaning if I measure from here to here, I would get the same number as if I measured the potential difference from here to here. Okay, so the current through is the same because there's nowhere else for the charges to go, and the potential difference across the two resistors in series has to add to the total potential difference here of the cell. In contrast, this is a setup of resistors in parallel. And now, because we've got branch points, the current leaving the cell can go this way, or it can go this way. And over here, it rejoins. So the current through, let's call this resistor 1 and this resistor 2, the current through resistor 1 and resistor 2 now have to add to the total current leaving or re-entering the cell. But if we go back to potential difference and think about that staircase analogy, here the energy per unit charge is being boosted up at the cell, and it's got to go down at each of the resistors. But we have two different loops by which that charge could shed its energy. One is to go this way through just resistor 1, and one is to go this way through just resistor 2. It never goes through both of them. And so if you think of the staircase analogy, the amount of upstairs here has to be equal to the amount of downstairs on each of these two resistors, and they have to be equal to each other. You can only go up as much as you go down, or down as much as you've gone up. So the amount of energy per unit charge shed here and here have to be the same, and they have to equal the amount gained here. So the potential difference across resistors in parallel is actually the same. Again, I think it makes the most sense if you think about it in terms of these staircases. Now let's quickly talk about ammeters and voltmeters. Ammeters measure current, and voltmeters measure the potential difference across something. Ammeters have to be connected in series with the circuit because we want the current going through the circuit to go through the ammeter as well. And we also don't want them to change the current. So if they are ideal, in the ideal situation, the resistance of an ammeter is 0. In contrast, a voltmeter is connected in parallel with a circuit, because we want to measure the potential difference between two different points, so we have to connect it to two different points. And if a voltmeter is ideal, no current will be flowing through it at all, so the resistance of the voltmeter, in the ideal case, is infinite. So if we come back up here, I've shown voltmeters connected in parallel across both the cell and here across both resistors, and if I wanted to measure the current in the system, I would have to put an ammeter in series with the resistors. So that's an introduction to resistors in series and in parallel and their properties.